Hey everyone, class 72, we just looked a little more at the Doppler effect and diffraction. So basically, I threw a scenario at you where there is a car, or excuse me, a car traveling. Person A is behind the car, person B is in front of the car, and person B hears a frequency of 450 hertz. All right. So if person B is hearing a frequency of 450 hertz and the car's approaching it, the car has to be emitting a lower frequency, right? Just think about it. Whenever a car approaches you, you hear a higher frequency than it's actually emitting. So if the person is hearing 450 hertz, it has to be emitting a number lower than that. It doesn't really matter exactly what you pick. I picked 400 because it was an easy number. Then the car is moving away from person A. So if a car is moving away from person A has to be hearing a lower frequency than the car is emitting. So just pick a number lower than that number. For me, number lower than 400, 350. There you go. Some people I saw, they picked like 350 for the car and like 250 for person A. That's fine. Generally, the frequencies wouldn't be a huge range, but I think that's just fine for our cases here. We're not doing any math with it. All right. So then you get those. So basically, again, the car is emitting a frequency. Person B hears a higher frequency because the car is approaching person B. Person A hears a lower frequency because the car is going away from person A. Also, as far as the wavelengths go, um, the waves as you approach person B get really bunched up together. Think back to that simulation we used. Check it out again. It's a really good one. Waves get bunched up in the direction of motion. And opposite direction of motion behind, they're all spread out. That's why when you have the longer wavelength, you have a longer wavelength, you have a lower frequency. We have a much shorter wavelength, you have a higher frequency. So what wavelength reaches person A? Well, person A here's a frequency of 350 hertz. The speed of sound in air is 331 meters per second. That's a constant. I don't need to give it to you. So the wavelength that they hear that comes to them is 0.95 meters. Now let's go to person B. What are they hearing? Well, they have a frequency of 450 hertz. So the wavelength that's reaching them is 0.74 meters. It's shorter, right? Now we exaggerated that difference here a bit, but you get the idea. The person B should be hearing a shorter wavelength because they're hearing a higher frequency. Now the true frequency is 400 hertz, and the wavelength that that person may hear is 0.83 meters. All right, so there are our values. So what if the car were going faster? What would happen? Well, the changes would just become more exaggerated. So person A would hear an even lower frequency, lower than 350. Person B would hear an even higher frequency, higher than 450. But the car, that wouldn't change. But the way someone put it I liked a lot was that the changes were more extreme or more exaggerated. Now, what if the car were going the other way? How would things change? But the same original speed. Well, if it were just going the other way, everything would just flip. Person A would hear a frequency of 450. Person B would hear a frequency of 350, but the car, that wouldn't change, the frequency emitted. Now, another topic here just to go over really quickly is diffraction. So diffraction is basically when a wave goes through a narrow opening, it spreads out. Okay, checking out the simulation there, we saw it a few times and you can check it out yourself. Or as a wave passes along the edge of a barrier, it also kind of tends to spread out. We'll get more into that with light, but there's another good example. So this one says, explain what happens to waves when they go through a narrow opening. Well, in the simulation, the waves spread out as they go through the narrow opening. How does this relate to like hearing people in another room? Well, think about it. Why can you hear people in another room? There's several reasons. The sound goes through the walls a little bit. Well, let's say sound didn't go through the walls. Let's say the walls were soundproof. If the door were open, when the sound waves go through the opening in the door, they would spread in all directions. Okay. So the answer to this one is obviously diffraction, because that's what we're talking about. Basically, why can the student hear the speaker? I want to talk about an incorrect picture that a lot of people think, though. So a lot of people think, and this is more what like a laser would do, but a lot of people think, let me get this going, that when the sound reaches the doorway, it kind of goes like this, and then it just shoots straight out, kind of like a laser. That is not how sound works, or else the student wouldn't be able to hear the speaker just in the other room. And you all know that you can hear stuff in the other room, even if you're not like right in front of the door frame, right? So this is not what happens. Okay, what actually happens is what I had depicted there. It spreads out in all directions. And that's why people can hear it all over. Another good example of diffraction is if waves hit a barrier. Okay, now we're going to get more into this when we get into light, but we'll talk about it right now. So let's say the waves are moving. Can't focus right now. All right. Let's say the waves are approaching this barrier. Okay, so here's another wave, and they approach this barrier. What some people might think happens is the waves just kind of go like this. But anyone who's been like at a beach and has seen a sandbar and the waves go around the sandbar know that that doesn't happen. These waves actually, they kind of, the way some people describe it is like they curl or bend as they go around. So when they get to the edge of the barrier, they kind of actually just go like this. This is also an example of diffraction. Again, we'll talk more about when we get to light. Actually kind of look more like that. All right, and they actually form pretty much. It's kind of cool. They kind of form like another wave. Again, all right, so there's diffraction for you. But for now, just understand that diffraction when a wave goes through a narrow opening.